I think we can go.
All right, very good. Okay. So I'd like to apologize for the 15 minutes delay or so starting the seminar. We had some technical issues, but Daniel, as always, very competent in technical issues. He was able to overcome them. It's my pleasure to introduce the speaker today of the TAO seminar. This is Professor Mark Miller, who is a professor of atmospheric science at Rutgers University. Me and Mark, we go a long way back in the days of the DOE ARM program. Mark got his PhD from Penn State, mid-90s. Actually, he was one of the first persons that actually studied marine boundary layer clouds, which is the topic of the presentation today. Probably the same island, but then Penn State, as a research team back in the mid-90s, conducted one of the first pioneer experiments for looking at this very important climate-wise cloud systems. So Mark did his PhD back in the mid-90s. Then he actually in '99 joined Brookhaven National Lab, and actually he recruited me at Brookhaven National Lab back in 2005. And then he joined Rutgers University initially as an associate, and then as a full professor since 2012. So Mark has done a lot of work in marine boundary layer clouds that you witness here in this presentation. And I have to say that he was also the first scientist of the first mobile arm facility, which is a pioneering method of moving an entire observing facility to remote locations. And Mark was the one that spearheaded along with the Department of Energy Atmospheric Radiation Measurement Program. So with that, Mark, thank you so much for coming, and we're looking forward to your presentation.
Thanks very much. I guess the title of my talk kind of talks about the complications in studying this particular cloud type, the complicated life of marine boundary layer clouds over the eastern North Atlantic. I just would like to thank the sponsors for this research first. And a lot of what we do is sponsored by the Department of Energy's Atmospheric System Research Program. NSF has also been very kind to support us in simulations that I'm going to show later in the talk on the Cheyenne supercomputer. Now let's see, there's the arrow right here. So I know we have an audience here that includes some absolute experts in the marine boundary layer. And we also have some folks who probably don't know that much about it and maybe would like to learn a little bit about how the cloud top marine boundary layer works. So I'll be giving some introductory material, maybe a little bit of history on how things have developed in the field for some time. I'll then turn to a series of observations and simulations to try to explain to you some of the difficulties in understanding cloud structure over the marine boundary layer writ large, but in particular over the eastern North Atlantic. I'll conclude with a little bit of a summary of some future projections, things that we think might be happening to this cloud system as time goes on. And then I'll draw a few conclusions. I would be helpless up here without the assistance of these two very hardworking graduate students. This is Melissa Rad. She graduated a couple of years ago. And Shushen Zhang, who is my current PhD student. A lot of what we've done has been done as a team and a collaborative effort. So I appreciate everything that they've done. So this is a well-traveled slide. And anytime you see any kind of presentation on stratocumulus in general as a cloud type, stratocumulus defined as low clouds, these are boundary layer clouds down near the ocean or the Earth's surface. This particular slide shows both continental and marine stratocumulus. This is from Rob Wood's paper in 2012. And if you'll look here, this is annual mean cloud coverage. So this is over the holistic year. And these oranges, the warm colors, represent, especially the deep oranges, these represent coverages of 50% or greater on an annual mean. So if you take a look at this and your eye sort of focuses kind of immediately on some areas here that I've outlined with X's here. These are sort of the traditional marine stratocumulus belts. These have been known for a very long time. These are regions that are involved with the upwelling of very cold ocean water along the eastern margins of the ocean basins. And they are capped by a thermal inversion due to subtropical cyclone, anticyclone subsidence. So it's like a little bit of a constricted layer in these areas where you see the X's. But I'd also like to call your attention to the fact that if you look at the slide in general, and these dashed arrows and this dashed sort of circumpolar line here are meant to indicate that it isn't only those traditional marine stratus regions that have a lot of coverage of marine stratus. In fact, it's you can see the mid-latitudes are very good locations for that. And I'd also like to call your attention, I'm going to point to this one actually instead of using a laser pointer. I'd like to call your attention to these transition zones in which we see very high amounts of annual cloud cover. And then as we move towards the tropics, so appreciably less cloud cover. Now, from a radiative standpoint, we might think about that a little bit. Think about the presence or absence of clouds over ocean. Okay, so if I place a cloud over an ocean surface, I've essentially put a low-level, virtually reflecting surface upon an ocean that is a good absorber for shortwave radiation. So if I take that cloud out of there, now photons right down to the ocean surface where they're absorbed. So the presence and absence of clouds, especially low clouds, over the marine environment, and I wouldn't just say the marine environment, but over the marine environment, we perhaps get the greatest contrast. The presence or absence of clouds is a huge radiative impact in Earth's energy budget. Now, the area that I have spent a lot of time studying is this area, the Eastern North Atlantic. I'm going to talk at the end of this talk. I'll be discussing a little bit about what the future of the clouds in this region might look like and why they might look that way. But I want to point out that this is an interesting region, not only because we have a transition from a fairly overcast situation in the high latitudes to tropical clouds as we move to the southern part, say down in here, we see a pretty large reduction in the annual cloud cover. But also notice that when we have cold air outbreaks, and these are often the locations where we find marine stratus clouds, these are coming directly from an Arctic that is changing. Okay, so obviously, as I'm going to talk about late in the talk, there are changes afoot here. The question is, what changes? So for those of you who are well acquainted with the marine boundary layer, you can take a nap. For those of you who are not, this is a slide which depicts some of the major processes that are at play in a well-mixed marine boundary layer. When I say well-mixed, I mean that we're looking at a fairly simple structure. Turbulence is kind of stirring up the boundary layer. It's fairly uniform. And the diagram progresses from left to right, showing many of the processes at play. On the left-hand side of the diagram, I indicate sort of the boundary conditions. So we have the fluxes from the ocean surface, and then we have the subsidence velocity from an anticyclone typically that caps, or whatever situation that's capping this particular boundary layer. That inversion is warm, dry air. Below it, in general, in the mid-latitudes and the high latitudes, you'll find cooler, moisture air in the layer from maybe 1 to 2 kilometers down to the ocean surface. Now, if I consider the radiative impacts here, then this next diagram over here shows you that we would expect, and we see infrared cooling to space at cloud top. And we also note that there needs to be a mechanism whereby we're going to mix up the boundary layer. And that mechanism is very important because it is that mixing that's going to transport water from the ocean surface, vapor, into the cloud. So we need to keep that sustained. Now, during the daytime, of course, we have to consider the fact that the sun comes up, and it's going to keep some of the vapor right in the top of the cloud layer. And that's going to be kind of important, as we're going to see in just a couple of minutes here. There is mixing between the inversion air and the cloud layer itself. This mixing is to some extent driven by the radiative balance at cloud top. We can't forget that the marine boundary layer is also a place that is microphysically quite active and quite sensitive. There is a layer of sea salt and maybe other aerosol near the ocean surface in the boundary layer itself. Those aerosols then nucleate into cloud droplets in the cloud, obviously. And then at some point, there is the production of perhaps drizzle, and roughly 80% of marine boundary layer clouds drizzle at some point. in their life cycle. And when that drizzle falls out of the cloud, it now evaporates in the subcloud layer, stabilizes the cloud layer, and it can affect this mixing process that extends from the ocean surface up into the cloud. And also, as we're going to see in a couple of minutes, a very important part of the way in which the cloud is sustained. This latter diagram over on the far right for you is really the key to the world. So this is from research done by Virendra Gate and a few of us back in 2014. We looked at a number of different marine strata systems. This is the radiative cooling rate that we see in the eastern North Atlantic clouds when we have single layer well mixed clouds. You'll notice those rates are about 1 K per hour in net. It's important to realize that if you see the green line there, and that's the long wave cooling rate at cloud top, and the red line there, which is that little tiny bit of heating in the vapor right at the top of the cloud, that radiative balance and that cooling rate cool parcels at the top of the cloud layer, causing them to become negatively buoyant, and they will sink. And that negative buoyancy may have an equilibrium level that's at the ocean surface. If those parcels sink down to the ocean surface where their equilibrium level is there, then compensating updrafts will be formed, and that will move vapor up into the cloud. It's important to, when you think about the way in which we develop clouds, we often have a sort of a continental bias. We think about warming at the surface that produces mixing and thermals and clouds. You have to turn your thinking upside down here. This is where the cloud layer is sustained essentially by mixing turbulent kinetic energy that's produced at cloud top by radiative cooling. So instead of warm air rising, really in this layer, the energy source is cool air sinking. Okay. So there is a well-known diurnal cycle in the marine boundary layer when it's well mixed. We talk about this because it's very important in understanding how we get changes in cloud structure. So you might think of a nighttime circumstance like this, infrared cooling, which is producing negatively buoyant parcels at the top of the cloud, turbulent kinetic energy production at the top of the cloud, that fueling this deep mixing down to the ocean surface, clearly moving vapor up from the ocean surface into the cloud, sustaining it. But during the daytime, when I begin to have a little solar heating right at the top of the cloud, that's going to offset that negative buoyancy that's created by long wave cooling. There's going to be a little warming. So in the net, we're not going to have quite as much negative buoyancy during the daytime at cloud top as we did at night. And when that happens, there is an equilibrium level for those sinking parcels at cloud top down that now does not extend all the way down to the ocean surface, but rather somewhere midstream, we now have an equilibrium level for these negatively buoyant parcels that doesn't include the lower part of the marine boundary layer. And this is really important because now we have this boundary set up, and when we set up that boundary, something interesting happens. Well, water vapor begins to accumulate down next to the ocean surface because this circulation is completely cut off from the circulation above because there is insufficient supply of energy from cloud top to mix the entire boundary layer. What happens? Well, the diurnal cycle causes marine stratocumulus in a well-mixed layer that now has this interesting disconnection. It causes a thinning of the cloud layer, and oftentimes, in fact, most times, almost a complete clearing. This upper layer becomes desiccated. We call this particular process decoupling, okay? And it is basically a process which results in a microinversion somewhere in the middle of the boundary layer that literally traps aerosols and vapor near the ocean surface and causes a desiccation of the cloud layer itself. And what this does is it establishes not only that we have a diurnal cycle, but that we might want to think about what happens in other scenarios in which we change the energy balance in the boundary layer. And so I'm going to start talking now about how you make a stratocumulus layer turn into something else. Okay, how do we make what happens to this cloud system as it evolves when it is decoupled. We're going to call this process cumulus coupling. So we're going to start out with a decoupled boundary layer, and pardon me, that decoupled boundary layer can be caused either by the diurnal process that we just talked about, or by having a boundary layer that's too deep to be supported and totally mixed by the amount of turbulent kinetic energy that's being produced at the top. So we're going to start out with this decoupled boundary layer, and we're going to look at the surface lifting condensation level. I have indicated here as an X, is now located up in that desiccated layer, which is disconnected from the ocean surface. So we have this stratocumulus deck, and we can imagine that as this progresses, we start to see that, well, okay, we're going to get a diminishment of the clouds, a desiccation of this upper layer. The clouds begin to get a little bit thinner there. But at the same time, we note that more vapor and aerosols are accumulating in this lower layer. And this lower layer is now, because of the difference in its vapor and the thermal differences above, is now a layer that has convective available potential energy. So that is building as well. The lifting condensation level, because of this accumulation of vapor, the surface lifting condensation level now moving towards the surface as vapor continues to accumulate. Pretty soon, the lifting condensation level is going to arrive in that lower layer. Okay, this is a conditionally unstable environment in which there is convective available potential energy. As that lifting condensation level arrives in that lower layer, there is the development of cumulus because of that. And those cumulus then rise up and replenish both water vapor and aerosols in the stratocumulus layer above. You see, I've depicted it as being thicker now, that stratus layer at the top. Also note that we call this cumulus coupling, but we shouldn't forget that outside those areas where cumulus is coupling with the stratocumulus, the boundary layer is still decoupled. Okay, so it's only through this cumulus coupling that we get a resupply of the vapor and aerosol that supplies and sustains the stratocumulus. It is this cumulus coupling stage that I'm going to focus on today. It is the part of the marine stratus system, as I'm going to demonstrate, that we understand the least. Okay. Now, I thought you might, pictures worth a thousand words, right? So here is cumulus coupling. This is sort of garden variety cumulus coupling in the marine boundary layer. This is in Graciosa Island in the Azores in the eastern North Atlantic. You can see the cumulus elements here. They're now feeding this stratocumulus deck. Where they're feeding it, you can see that darker color indicating those stratocumulus are being replenished by the cumulus. Now, this is sort of the standard fare cumulus coupling. I'm going to demonstrate this is one of two important modes of cumulus coupling, the second of which is even least understood than the basic variety I'm showing here. So one other way to have this whole process work is to change the boundary conditions. As I move towards the tropics, I warm ocean water. I move southward in the Hadley circulation and reduce the amount of subsidence, which is now going to deplete the strength of the inversion as I move in that direction. And if I begin with a well-mixed boundary layer here, let's say we begin this in the northern latitudes, okay, as I move into situation where I increase the sea surface temperature, I reduce the amount of subsidence, the boundary layer becomes decoupled, and eventually we get cumulus coupling. And ultimately, there's so little subsidence and so much latent heat release as we move towards the tropics that we have an overwhelming amount of convective latent heat release. Okay, so what happens when we move from the mid-latitudes, the high latitudes, to the tropics across that transition zone in the annual mean cloudiness that I showed you in that slide from Rob Wood early on, is that we have a slow transition from a marine boundary layer that is driven in the high and mid latitudes by the energy balance at the top of the cloud layer to ultimately down in the tropics, a boundary layer that's driven from below. It is that middle ground, that cumulus coupling ground, this ground, that you might imagine, and I often think of this by, just if you just sit for a minute and think, how tough is it to parameterize, to put together an understanding for a model that has a fairly significantly large resolution, like a climate model. How difficult is it to parameterize a situation in which you have two cloud types? We can think about one. Well, it might be easy enough to do the single layer stratus. And we know a lot about cumulus convection on the other side of this. What happens when they both exist? Okay, how does a model handle it? And especially, how does a climate model handle it? So this deepening warming process has been known for a long time. Pablo's talked a little bit about it here. And you can see here, it was depicted even back in 1995, when it was first really uncovered the fact that cumulus coupling was the intermediate stage between solid stratocumulus in the mid-latitudes and cumulus near the tropics. So
what's the diameter of one of those cumulus?
I'm going to get to it. I'll answer that question in more detail than you probably want to know. So I'm going to ask a few questions about the cumulus coupled environment. And the first thing I'm going to ask is, how is it represented in models? Now, I could pull out one of the IPCC models and we could go at it that way. Another way of looking at it is to ask whether cumulus coupling, how is that represented in a reanalysis product like ERA5? We think of an ERA5 reanalysis as maybe being our best, or one of the reanalysis products as being our best estimate of the state of the atmosphere at some given time. It's a combination, basically, that looks a lot like a climate model. It has a base that is that. It has a 30-kilometer grid spacing, so this is sort of a lower resolution model, 137 levels. It combines not only advanced models, but also assimilates historic data, other sources. This ought to be the best guess. This thing ought to be able to produce cumulus coupling. Given if we really know how this works, ERA5 should do it, right? Now I'm going to show you some convective resolving model results a little bit later. We'll get to that as a separate topic, and I'm going to talk about this subject of does WRF produce these things called MBLCC. This is the second mode of cumulus coupling, and I'll refer to that a little bit later as well. So I'm going to employ data from my favorite site ever. There has never been a better field site than the Eastern North Atlantic Observatory. I'm sure I could get a disagreement from some people in the audience, but I love this site. This is on Graciosa Island in the Azores. Here are the Azores, like a second home to some of us. So this site is well equipped. I'm not going to get into the specifics of all the measurements that are made here. Let's just put it this way. You'd be hard pressed to find another site that's better equipped than this almost anywhere. Okay. So when I look at marine boundary layer clouds over the Eastern North Atlantic, and I'm going to make a few people in this room probably nod their head yes and maybe even chuckle. If you want to talk about complicated cloud systems, this is the poster child for it. These things are mode switching. And here I show, this is basically just over a 24-hour period. This is radar reflectivity in the contours here. The dots there are a laser salometer, which is detecting the optical cloud base. These are 6-hour chunks of time extending over 24 hours. And when you look at this, sometimes you get single layer stratus, sometimes you get this very bizarre structure. The mode switching is mind-boggling. A couple of hours go by, you have one mode. Suddenly another mode, oh, you launch a new radiosonde. Conditions aren't that much different. So the mode switching can really be confusing. And as a result of that, 4, 1, 1, 3, 2, my student Shushen and I came up with a way to use a K clustering algorithm. I'm going to show you the results of that in just a minute. In other words, how do you sort out this stuff to actually analyze it? I'm interested in one mode here, cumulus coupling, but there's all kinds of modes in there. And over a 6-hour period, which is relative to something like ERA 5, we need to pick out a mode that's dominant. In order to do that, we used a clustering scheme, and you can read all about it in our paper. But essentially what we did was we came up with a 3-parameter clustering scheme based on my experience and a little bit of toggling around with factors with my student. And we could then, for each 6-hour period, we eliminated those periods in which flow was coming over the island of Graciosa. We don't want that interference in this. So we're going to be biased towards flow coming from the Arctic or that area, the northerly flow down into the eastern North Atlantic. When you take those periods, you can put together a pie chart like this. And what you find is that when you look at the different cloud types around here, and I'm going to get to the ERA5 simulation of this in just a moment, you see that cumulus coupled, single layer, and broken clouds, well, they're not really exactly equally weighted, but they're pretty close to equally weighted. In other words, they're actually more single layer stratocumulus than anything else, but there are not that many more than there are broken clouds and cumulus coupled stratocumulus. This is a perfect example of what the transition region should look like. We should have sometimes when that transition zone is north of the area, sometimes when it's south, sometimes when that cumulus coupling zone is right over eastern North Atlantic. So I'm not surprised by this. I'm actually in some sense pleasantly surprised, despite the complexity that I see in those clouds. I am reassured that I have in fact located myself in the transition region with eastern North Atlantic. So now, okay, great. We know how many of these 6-hour periods were cumulus coupled during this 4-year summertime period. Well, let's ask the question, how did ERA5 represent the different types of cloud? Now you'll see that I have up here only those, this is cumulus coupled results only. And you might say, well, thank you very much, Mark, but how did the model do when we had single layer stratocumulus? And how did it do when we had broken clouds? Those were other cloud types there. Here's my answer, virtually perfect. ERA5 does a terrific job in this region when you have single layer stratocumulus or when you have cumulus. When you have cumulus coupled stratocumulus, not so much. In fact, if we look here, I'm sorry, these colors are kind of not as bright as they are on my computer, but let me just point to what we have here. This is specific humidity, and this is profile. Okay, the green circles here for all of those 277 6-hour periods in which we had cumulus coupled stratocumulus. What did ERA5 think the specific humidity profile looked like? That's these green circles, and this is the range during that period. Here is in blue the mean from the ERA up I'm getting this confused. ENA, the ENA observations, and here's the range. What you see is that ERA5 fails to capture the decoupling. Okay. This can also be seen in the profile of the equivalent potential temperature. This is a variable which is conserved in all conditions, including drizzle. And here again, ERA5 would like to represent the boundary layer when it's cumulus coupled as some sort of well-mixed thing. But it's not well-mixed. Okay, it's not well-mixed at all. And then we look over here to how did we do with cloud fraction versus height. Here we see, again, the green and bars are ERA5. We see that, again, ERA5 underestimates pretty drastically the amount of cloud cover that's present in this particular region at ENA. And I expect it to be more than that. Now, am I surprised to see that this model produces less clouds? No. The literature is full of papers showing that in general, in the marine boundary layer, in this type of cloud system, models produce too few clouds. So there is something we call the too few, too bright problem. In these latitudes, we generally produce too few clouds. We move towards the tropics, those clouds become a little too bright. So too few, too bright. This is the too few problem. ERA5 has it, and I'm going to show you that I can even do better using even a more highly resolved model, and I'm still going to have this problem. And I'm going to show you that in a little bit. Now, I wanted to call some attention to this is a partial result from a paper that Katya published back in, I guess it was 2020 here. And what I want to call your attention to is this. Actually, I should go back and then come forward here. Notice the problem here seems to be in vapor. And you would imagine that, well, okay, it's water vapor, it's decoupling. So we think of water vapor and clouds, you know, so we start to connect the dots here. And if we look at this paper by Katya, this is not the entire study. Their study was a study of the cloud structure at the eastern North Atlantic and what things controlled some of the precipitation in that region. All right. And I want to call your attention to this diagram here on the left. And these are a few of the factors that were examined in that paper. This is the one that I want to call your attention to because it shows a very strong dependence. So here's the cloud depth and the cloud boundaries. And you can see that as the surface relative humidity is less and less and less, the cloud boundaries and cloud thickness respond to that. So this is telling you that this observation is very consistent with a problem that you might think of being existing in the ERA5 model if its inability to get the moisture profile is as acute as it seems in the plot that I just showed. What I'm saying here is that it's all about the moisture and it's all about the decoupling. And if you don't get that right, you're not going to get the clouds right. Okay. So that's reinforced by this result from Katya's paper in 2020. Now, the last part of this talk essentially is about the second mode of cumulus coupling. Okay. So I showed you sort of a garden variety cumulus coupling. Okay. A few cumulus clouds rising into stratocumulus. Look like something you could actually see around here at times, and you can. But back in the early 90s, we knew even before this, there were mesoscale circulations at work in the marine boundary layer. So this is some early data from that experiment that Pablos was referring to back in the early 90s. These hatched areas are basically where a cloud radar observed clouds. This is height. This is 1 hour in time. This is one of these structures at night passing by, and a scale of about 10 kilometers here. There is a cycle going on. You can see that best. You look down here at the wind versus time. You see this sort of cyclic circulation suggesting, so we already knew this, but maybe adding to it, that there's a lot of mesoscale activity in the marine boundary layer in this area, and in fact, in most all those areas. But over here on the right, we sort of divide this into closed cellular when it's totally cloudy, open cellular. I'm going to show you an example from another paper in a moment with this as well. But over here on the right is the cumulus coupled situation. And here we have 10 kilometers here, and you can see the scale of this. This is much larger than a single cloud. Okay, so when we think of cumulus coupling, we tend to think of a few random cumulus rising into the stratocumulus. But these data and visual observations back during this experiment indicated these things called marine boundary layer convective complexes that were organized on much larger scales. Okay, so we've known about this. Now, there's been some recent work on closed cellular convection. And this is some work in which Mike Jensen and colleagues looked through years of data, basically, at Eastern North Atlantic site, picked out 24-hour periods where we had one mode of convection, closed cellular convection, here represented. Here we have radar reflectivities. This is 24 hours, this is height. You can see that if you look close at these satellite images, which are one representative period for this, you can see there is cellular structure here, even when we have this nice stratocumulus top boundary layer. So even then you have mesoscale circulations, just as we showed back in the early 90s. That same paper showed basically open cellular convection, same sort of climatological study. This case, open cellular because there are breaks between the clouds. Remember, this is a big radiative difference between open and closed cellular convection. This is a huge radiative difference. Notice this lace-like structure that you see, open cellular convection. So we've known about these mesoscale circulations. Now, with the ENA site, we know more and more about them. We can do consolidated things like the Jensen paper, and we can do things like was done in that paper. We take the thermodynamic situation and we say, well, what is the average closed cellular circulation thermodynamic profile look like? And what does the average open cellular convection profile look like? And the big difference here is, and you can see it in the potential temperature, but basically, notice the mixing ratio is indicating on average this is decoupled. So what this tells you is the open cellular convection and its mesoscale circulations are operating in a decoupled marine boundary layer. And this is where, again, I point back to that ERA5 result where we have trouble in being able to replicate the structure of those clouds. So if you don't believe me, maybe you'll believe a picture. All right. So here's garden variety cumulus coupling. All right. I showed this earlier. Cumulus. Then I want you to look closely at this bottom photo. Maybe some of you can't see it in the back, taken from the same island, basically. Notice this monster off in the distance here, where you see what looks like a bunch of cumulus, but you can barely tell because there's so much drizzle falling out of this that you literally can't resolve the individual cumulus elements. And there's a rope-like edge to this thing. So this thing has a circulation. It reminds me, if I didn't tell you, if I showed you this picture and I didn't tell you this was from the marine boundary layer, you'd probably say, well, this looks like a deep convection, some mesoscale deep convective thing that you'd see in the tropics. Okay, it's got a well-developed anvil, everything that you'd expect. Only this is only 2 kilometers. Actually, this is only 1.4 kilometers deep. So we've got these mini thunderstorms, and they're organized very much on the mesoscale, and we don't know very much about them at all. Well, we're going to know more. I'm going to show you a little more. So some recent work, we're trying to figure them out. So how many of them are there? How frequently do they occur? What is their scale? Those are basic questions that we're trying to ask about a structure that's really important in this and other regions. I'm talking about the Eastern North Atlantic. I have talked to many folks who were on the Southern Ocean cruises. They see them there as well. They're pretty prominent in these transition regions. So we wanted to ask, what are the scales? So let's just get some basic information. How big are they? All right. So we went through my student. This is a work with my student Xishen Zhang. So we created an algorithm. I won't get into all the details. This algorithm identifies these structures and picks them out and classifies them by scale. I won't get into all the details. You'll soon be able to read about it in her paper. But beta, gamma, alpha scales, these are all the mesoscales. Just to remind you, gamma is 5 to 20 kilometers. So these are relatively, not huge structures. Beta, 20 to 200. Now I'm out here to alpha. I'm just going to say that basically we're starting to piece together the flow, the ebb and flow of these things. And one of the things, using time-space conversion, we are finding that roughly 50% of the beta scale structures form after a gamma scale structure. Now, what does that mean? I'm using betas and gammas. What I'm saying is I get a small scale structure followed by an increase in the scale. Okay, so as we move through the structural elements here, if we get a small scale structure, not long after that, we get a larger one and a larger one and a larger one. So either conditions are changing in the boundaries, maybe not so much in what we see, but there is something else at play here, some organizational aspect that I just want to mention here. I also want to mention that alpha scale structures, we sort of have now linked these big, long-term things to funnel structures.
What's the quantity being plotted on the color scale?
I'm sorry, it's cut off because yours truly cropped this morning and was a little over aggressive with the cursor on my trackpad. This is reflectivity. I'm very sorry. This is radar reflectivity, and these numbers are 20 down to -40.
Got it, thank you.
Apologize. I'll have to be careful with that trackpad. At any rate, this is part of it. The next thing is, well, how many of what? All right. Well, it turns out that gamma and beta are really the predominant two scales here. Okay, gamma, of the roughly 500 of these we did, 226, we're basically gamma scale. That means most of them were in these 2 to 20 kilometer range. But the larger scale structures, all the way out to 40 kilometers, you're still getting a lot of these that are 40 kilometers in extent. And then you can see it slowly tapers off, and down here is sort of the frontal scale. So what we're learning here is that there not only do we know a little more about the scale now, we also know there are a lot more of these things than we really thought initially, I think. And right now, we crudely estimate, based on some sort of back of the envelope stuff, that about 40% of the time when we have cumulus coupling, these are the mode. It's mesoscale organization on this larger framework. So now to the last part of the talk, which is what about models? Can we bring to bear the best and brightest of the models that we have right now? I'm sure there are some people in here who would probably chuckle at that, thinking, well, I have a better model than this. But let's start with early modeling efforts for deepening warming. This is Steve Kruger's 1995 paper, followed closely thereafter by Brotherton and Wyatt's paper in 1997. These were the two papers that sort of defined 2D modeling that showed that you would get cumulus convection as the deepening warming process was at play. Okay, these, while they represent cumulus, there's nothing in this kind of model that could say anything about mesoscale organization. I mean, this is a fairly simple model, right? I mean, you can't really say, basically in the Kruger paper and in the Brotherton paper, we talk about decoupling and we talk about cumulus convection. There's nary a word anywhere, nor is there the capability here, or was there the observational capability in 1990, in the 1990s, to say anything more than we saw them. That's basically it. Now we have some observations. I've shown you those observations. Let's see what we can do with a state-of-the-art model, WRF. When we explicitly resolve, we're going to call this cumulus resolving, and we can all get into a big debate about how big a cumulus element we need to actually resolve to get this to work. The answer for us was what we could get with the Cheyenne hours that we had and the number of tests that we had to do. And so the domain that we're going to consider is here. There are two domains centered on Graciosa Island. The inner domain is 1050 by 1050 grid points. You can see we're using, basically NCEP GDAS boundary conditions. The horizontal resolution is what I really want to point out. We're gonna do this regional simulation with the inner domain here having 1300 meter resolution. So this is going to resolve larger cumulus elements, not all cumulus elements. You might say, well, what about those other ones? Do you resolve them at all? The answer is yes. The PBL scheme does have those smaller convective elements. Not sure how well they're represented, but we're interested in the ones that are totally resolved here. Okay, the ones that are 1.3 kilometers and larger. So, these are cumulus resolving. These are compatible with the observations at ENA. I won't get into all this, except I will say we did two simulations of cold air outbreaks where we often see these structures, one in 2017 and one in 2018. They were both 72-hour simulations. You can read all about them in our paper. We probably put more detail in there than most people really care to know. So, and now the big question everybody always asks, well, what parameterizations did you use? So here they are. Thompson aerosol aware microphysics. In the interest of time, I won't get into all the details of that. It has a climatological aerosol distribution in it. It does do some microphysics that relate aerosol nucleation to cloud droplet processes and then drizzle. Planetary boundary layer. Mellor, Yamada, Nakanishi, and Nino. This was the key to the world for us. I'm going to stop there for a moment by saying that we began this experiment by using another PBL scheme, actually two others. And we got no clouds, or very few. We didn't get no clouds, but when we looked at the clouds that we were getting, they were few and far between, causing us really to spend about 4 months scratching our heads. You know, how do we fix this? What do we do? Finally, we decided after playing around with more and more parameterizations, this one actually works. And we used classic long wave, short wave. Now I'm going to say it works, but I'm going to put a caveat on that. It sort of works. All right. Long wave, short wave radiation, sort of standard. The surface layer is according to the same PBL scheme that we looked at. There is very little land surface here, but NOAA was used for that. You might ask, again, I'm just going to reiterate that if somebody's going to ask me the question, why these? Because they worked. That's why. And we spent 400 hours of computer time trying to figure that out. So I don't have a whole lot of time. I just want to show you that the too few problem does exist. So these are ENA observations. So in those simulations, we picked out the Eulerian point in the simulations where the ENA site was. And we plotted here the cloud boundaries and the vertical wind speed from observations from the Doppler LiDAR. And this is WRF for one of the two simulations. You can see the cloud structure here. The color contours are vertical velocity. You may not be able to make them out as clearly, but I'll tell you there aren't many colors here, and there are a lot here. So we were seeing a lot more agitation, turbulence in the boundary layer than WRF seemed to believe that there were. And you can also see that here we have a period of solid cloud cover. This was called the golden period, one of the golden days during the ACNA experiment. This is that period. Notice WRF has clouds, but not the right kind of clouds. Okay. And then over here is another case here, probably showing when we compare the observations again. WRF has clouds and it has similar cloud structure. When the forcing is pretty significant, the clouds look fairly similar. When we get to this marine stratus, not so much. And you can see very turbulent subcloud scale structure in the observations and even a different cloud type. So, well, I'm not going to blame WRF because maybe WRF got it wrong in the sense that maybe WRF made the transition sooner. Okay, maybe WRF was just wrong in positioning the transition to cumulus. Maybe that was the issue. So here are some attempts to ask that question. And the answer was, yeah, it looks like that was the issue, but WRF really transitioned way too fast, very much too fast. Here are, these are sort of pseudo satellite images from the modeling effort. Here you can see the cold air outbreak. We're going to do a little bit of a Lagrangian look at this structure here. From the solid cloud cover here that you see, we're going to progress down and watch this transition and see how the model handles that movement from solid stratocumulus into broken or cumulus coupled stratocumulus. So we didn't get the, and right here is ENA, it's in the middle of this. We didn't get the location right, but the model seems to at least know there's a transition going on. And it's doing something kind of interesting. It's producing these sort of open cellular like structures that we see in the observations. So let's look at these Lagrangian trajectories kind of in holistic view. I'm going to just, there's a lot here. I'm just going to put some boxes up to point out a few things here. This is the evolution. This is a Lagrangian trajectory. Those three long circuits that you saw, here are the trajectories for those. And let me just flip through what the observations show here. The very first thing that you see is you begin to see some temporary fractures in the cloud deck. And if you look closely, you start to see some indications that cumulus are starting to form below the stratocumulus, okay, in the model as it moves south. So the clouds begin to break up from the base. This was, for me, a shining moment when I thought, holy mackerel, the model knows about it too. This was totally chaotic. I mean, we saw this period in the simulation where the model was just, there were clouds everywhere. Clouds up high, clouds down low, clouds in the middle part, cumulus elements mixed in. So the model, and when I looked at this, why was I so happy to see this? This is 100 kilometers. That's what an ENA, that's what the average day at ENA looks like. It's crazy. It's chaotic. It's transition. The model seems to know about it. Maybe it doesn't have all the details right, but it surely knows about the chaos. And then last, let me get the arrow right here. So we started to see some downdrafts in there. They became pretty prominent. And what else does the model know? When you start to see these fluctuations in the latent heat flux, and I can't get into all the details. What I'm saying is the model also knows there's some mesoscale stuff going on. All right, there's a feedback. All right, and then lastly, erratic. I'm sorry, I missed that. Got too quick on the draw here. Erratic fluctuations, and I mentioned those. But here was sort of the crowning achievement of WRF. WRF does know about marine boundary layer convective complexes, and there they are on the far right hand side. So WRF, when you resolve the larger cumulus elements, WRF wants to organize them into mesoscale structures, and that's what you saw. What we're now trying to figure out is how does WRF move them into that direction, and how does that relate to what we actually see at the site? In other words, does WRF have the right idea or not? And so we're trying to figure that out. The beautiful takeaway here is that at least we have something to compare. We didn't have that before, and I think we're making good progress in terms of not only understanding the structures because we have better observations, but I really want to highlight, for me personally, input from the model has been really key in terms of trying to understand how this whole process really evolves. Just last couple things here. I've only got 2 more or 3 more slides. I'm just going to show you that when you look at these structures, this is a volume rendering over here on the right hand side. These look like thunderstorms. So here's the solid layer of cloud in WRF. It's the volume rendering of cloud liquid water. You see the transition to smaller structures and then the increase in scale as we move south. They become larger and larger. Okay, that's very consistent with what we see from the observations. Won't get into much this. I just want to say I've got 2 or 3 more slides and I'll call it a day. But these are, I guess I should flip back here for 1 second. Whoops. These 3 boxes, I'm just going to take a cross section through them and say, what is the scale? I just want to see how the scale is changing from here down to here. How are we growing these mesoscale structures? And here we indeed see that. This is the far northern box, a little bit further south. And then finally, now we have these multicellular convective complexes, just like we're seeing in the observations, building much more pronounced stratocumulus deck, as we saw in this last depiction right here. You can see that as these structures become larger and larger, so too does the stratocumulus deck that they feed. And that shouldn't be understated. So as they get stronger and as they get larger, they produce a larger area of stratocumulus, thereby blocking more and more radiation that otherwise would have slipped between those cumulus elements. Okay, so there must be some advantage to this. There must be some way this engine works. How that works, that's some of the stuff we're trying to figure out. What is the advantage of this mesoscale organization? Lastly, 2 slides to talk about the future. This is a slide. Now, I guess maybe I should show you the second slide first, but let's talk about this first. So this was a summary that Chris Brotherton published in 2016, showing possible changes to marine boundary layer clouds in response to climate variation. Okay, so we could change things about the radiative budget, and if we do that, this was a bit of a modeling effort as well. We show that the stratus maybe gets lower and it changes its thickness. we might be able to produce less substance in in our new climate system as it evolves. And if we do, well, processes conspire in that case to raise the top of the stratocumulus and make it thicker. Here maybe we could make it a warmer sea surface temperature, or we could dry out the boundary layer, in which case we do have a bit of a change, but it's mostly a cloud base. And then finally, we could toy around with the inversion strength. We could also change the stratus structure. Now, that's interesting because this was a paper published in 2016 by Joel Norris and colleagues. This is a paper that looks at 1980s to 2000. We're looking at 30 years worth of ISCP data on the top, and 30 years worth of series URBI data over a similar period on the bottom. This was a Nature paper that was written. The darker colors here, the orange, the warm colors, showed declines in cloud fraction. Okay. There, you may not be able to make it out. There's the East Coast. There is Spain and Portugal. There are the Azores and the Eastern North Atlantic. Both independent satellite summaries showing reductions, significant reductions in cloud cover over the Eastern North Atlantic. So I'm going to leave it right there, just by finishing up with the following statement. We really need to know more about this, because this is critical. And I'm saying that not because I'm a marine stratus person, but really because when you see that level of change of cloud fraction, you got to start to wonder what's going on and how these forces are conspiring to do that. So what I'm trying to do in my research, and what we continue to do, is to try to understand cumulus coupling, because in my particular view of the world, I think a lot of the too few problem that we see in marine boundary layer clouds really has to do with too few cumulus coupling clouds that are represented correctly. That would be my take on it. I could be wrong. I'm not saying that's the right answer. I'm just saying it is a plausible answer. Let's put it that way. So I hesitate to draw conclusions, but I will. I guess my conclusions are that my title was correct. The complicated life of marine boundary layer clouds over the Eastern North Atlantic. I would probably extend that a little bit and say the complicated life of marine boundary layer clouds, period. Okay. So we have improvements. We're getting better at this. We're working towards a composite structure of marine boundary layer convective complexes. That's been a great hope of mine since the early 90s, and many of us actually. So I think we're getting close to that, because we now have the observations, we now have the model capabilities to really understand this a little bit better. For those of you who are marine stratus aficionados, I would really love to have talked about cloud top entrainment instability, because it's one of my favorite topics and its relationship to marine boundary layer convective complexes. I shall leave that for another day. More recently, drizzle, we've now gone a little bit further, and we now believe that at least 2 of the 3 organizing principles that we hypothesize for these, we have some evidence circumstantially at the very least to show. We believe the amount of drizzle evaporation has a key role in the organizational aspect. We also believe that low-level wind shear, oddly enough, similar to what you might think about when you organize severe thunderstorms, also has a role in this. We are contemplating the role of cloud top processes right now in helping to form downdrafts that are well sustained and keep these things very well organized. And we point out that studies in the Eulerian framework are useful, but model results are fairly clear in showing us that the evolution, the cloud that's above your head in the marine boundary layer, does not result from the forces at your feet. It results from the forces that were way upstream. And you have to have all of that information along the pathway before you can really talk about the life cycle of cumulus coupling. And that's where the model comes in. I'm sorry if I spoke a little bit longer. I'm highly enthusiastic about this topic, but I really appreciate your attention. And thanks very much. It was a great opportunity. I'd love to talk about this stuff anytime and in more detail.
you so much, Mark. That was great. We have a little bit of time for questions.
Don't tell me I scared everybody to death.
No,
I got a
no.
question. You had a distribution of your alpha, gamma, and beta. Is that, but it seemed like it was kind of an arbitrary coupling, but when I look at that, it looks like a Pareto distribution almost, or some power law relation. Have you done any functional fit or statistics?
We have a, I guess the best way to put it is, we do have a functional fit for this. However, this particular chart that I'm showing you was based initially on an assumption that the wind speed was 10 meters per second to make the time-space conversion. We fit these. We don't think that will pass. It doesn't pass my muster. And I went, Shushan and I sat down and we said, this was a great start. Guess what? We have to put the real fit. So in order to do the time-space conversion and produce that fit, which we will, we really need to get that time-space conversion. I don't think it's going to make a huge difference, but I don't think we want to say anything about it until we've done that.
You what?
To follow up Ernie's question, did you look at the area distribution? Here it's the size distribution, the coverage distribution, because I would tell
Yes.
like the radiative.
Yeah, I think that's a really open area for us in terms of what we want to do. We really believe we need to bring satellite data to bear on that for that very reason, because even though we do have these nice cross sections, you're right, we don't know how big the actual aerial. Now we have the model result. The model result definitely shows us that stratocumulus occupies a larger area atop these things once they develop more. But that's the model's view, and I don't know what the real view in the atmosphere is. But the aerial coverage of these, I can think of them as in a radiative respect, being a very important question to answer. Actually, is that the aerial coverage? Yeah, because I totally agree, and we see these things a lot in the satellite photos. But it's really important to know how many of these things, how big a stratus deck do we feed? That's what I think is really interesting. Also, there was a subtle indication that the upper level winds, the boundary layer, were shearing off the tops of these convective structures, almost like thunderstorms and an anvil preceding it. So the aerial coverage could well be sensitive to something like that as well. I wouldn't be surprised at all, in fact.
Thank you.
Yes. The observations that you favor in the North Atlantic, the Azores, I think you said, are they incorporated into the Era 5? Or is that totally separate?
The soundings may be, but the cloud observations themselves, no, none of that. The soundings and surface observations, I don't know actually, I would guess they are.
I'm always confused about that, but to what degree are the observations actually, to what degree is it modeling data points versus observational data points? I don't know.
My gut reaction to that is, if you're right, and I think you probably are, they probably are assimilated in there. Doesn't make much of a difference in the model, because the model still gets the problem. So even though you're assimilating, and you raise a really good point, even though we're assimilating this stuff, we have one data point, maybe the model physics basically are taking over, and I would guess they probably are, because you have one data point here in the middle of the Atlantic, maybe a few aircraft observations and some other things, but it's not exactly a tightly constrained system there. Your point is a good one. I think they probably, I'm almost sure they are assimilated. But I think it's interesting that the model still doesn't really want to do anything other than produce a well-mixed layer.
I think it's interesting that the observationalists tend to talk about ARIS model, and the modelers tend to talk about ARIS observations. And I'm not sure how we should really talk
Well,
about
you're right. It's kind of a little of both. It bridges the gap. In a sense, it is. You're exactly right. It's not exactly a model. It's not exactly the observations.
It's millions of observations incorporated.
It is.
Right. So
it is. And it's satellite observations too. So you might also say, well, ERA5 may know more than just the ENA site from satellite retrievals as well. Yeah, you raise an excellent point. I mean, the degree to which the observations here, and whether this really is a model, or whether it's really observations is a bit of a debatable subject, and that might be something we could probably get a round table with two sides on.
Do you want to have the last?
No, just comment that I've seen this recently. Nice work in like Bill Stevens and Sandrine Bonny kind of about this AI kind of classification of clouds, like remember like fish, flowers, and gravel and sand and things. Can you look at that area? Because I think it's very interesting that even though, like, for example, look at the area, but actually this area of clouds can be distributed completely. Even though they have the same area, they're actually very different how they appear on satellite imagery. Like some of them, like mesoscale organization.
Yep.
And they actually found some very big differences, fairly big differences in the underlying conditions that each create those structures. So it'd be interesting if you.
Yeah, I'll take a look at that paper. I know Bjorn was doing a lot of work in this area at least for a while, but I guess he's back doing it now. So I'll have to, yeah, I mean, it's really true. I mean, this is no panacea in terms of what the AI that we use is our best effort. But no matter what you do with an AI scheme, you're going to have to put some subjective.
Oh, no, my point is that it's organization, but it's not the whole organization, even if it's mesoscale, they're all different.
Well, that's probably
So it may look like a large thing, but those large things are different.
that
And not just appearance, but underlying meteorology. So there is actually probably more complex issues than we think.
Oh, I would not disagree with that at all. In fact, I guess I'd like to say that one day when I hang up my research hat, I'd like to say that at least I push things, or we push things forward a little bit. By no means do I think we're close to the end on this puzzle. This is a real puzzle.
Okay, all right. Thank you so much for the Q&A, and let's thanks one more time the speaker.